Hello everyone, my name is Song Yu. Today, I'm excited to present you my final year project on deploying a speech recognition system using Kubernetes cluster and infrastructure as code tools, including Terraform and Terragrant. This is an outline for today's presentation. Firstly, we'll be going through the background of this project, the technology stack that we'll be using, and then we'll be going through the analysis and design solution, as well as the implementation with a short demonstration. Finally, we'll be concluding this project and provide some suggestions for future works. Now, let's start with some background information. There's an open source automatic speech recognition system called Kaldi, which is developed using Python. It can transcribe audio input into text output, and multiple language models have been developed by the NTU Speech Lab. The application itself is containerized using Docker. With the application developed, we have some questions in mind. For example, how can we deploy the application on cloud platforms so that our clients will be able to access the transcription service? And how can we create multiple environments to improve the software development process? Now, to answer these questions, we need help with some powerful technologies. The technology stack used in this project includes containerization, infrastructure as code, cloud computing, and monitoring. For containerization, we use Docker, which packages applications with their required dependencies, provides consistency across different environments, and enables efficient deployment and scaling of applications. We also use Kubernetes as a container orchestration tool for managing our applications, automating deployment, scaling, and management of containers, and providing high availability, scalability, and fault tolerance. We also use Helm, which is a package manager for Kubernetes applications. It is used to streamline deployment, management, and versioning of resources. It also facilitates with reusability and consistency in application deployment. For infrastructure as code, we use Terraform, which is a popular tool for provisioning resources. It uses a declarative language for defining and managing infrastructure. It also enables automation, versioning, and reproducibility in infrastructure. This graph gives you an idea of how to use Terraform. Firstly, the cloud practitioner or the developer needs to write the infrastructure as code into configuration files. Then, using those configuration files, we need to run the Terraform commands such as plan and apply, so that Terraform will be able to communicate with cloud providers and call the APIs to create resources on our behalf. On top of Terraform, we also use Terragrant, which is a wrapper for Terraform. It simplifies the multi-environment configuration, state management, and reusability. It also provides dry or don't repeat yourself approach in Terraform deployments. In this project, we mainly use Terragrant to help us create multiple environments. Terragrant leverages the code that we create using Terraform and abstract away the details. We only need to provide environment-specific values to create the environments that we need. For example, production, QA, and stage environment as shown in this figure. In terms of cloud computing, we use Amazon Web Services, or AWS, which is a popular cloud computing platform offering scalable services such as storage, computing, databases, networking, and more. AWS enables on-demand resources, pay-as-you-go pricing, and global availability, which is exactly what we need for this application. For monitoring, we use Kubernetes Dashboard, which is a web-based user interface for Kubernetes clusters that provides visual monitoring and management of resources, enabling easy navigation, inspection, and troubleshooting. We also use Prometheus and Grafana, where Prometheus is an open-source monitoring and alerting toolkit that collects, stores, and visualizes metrics from applications. And Grafana is a popular open-source dashboard and visualization platform that enables creating custom dashboards for data visualization and integrates with Prometheus for monitoring and alerting. Now, let's talk about the analysis and design solution. The traditional approach to deploying an application on cloud platform requires us to use YAML files. YAML files contains the configuration of the resources that we need to provision on the cloud platform. However, YAML files can be hard to read and maintain, and it can be very hard for developers to keep track of the changes applied through YAML files, and it can be very hard to debug. Alternatively, we are able to use the Cloud Platform GUI offered by cloud platforms. For example, AWS provides a web-based application called AWS Console, which can be used to create resources manually. The user needs to know what resources that we want to provision and constantly navigate through different UIs using the application. As you can see, it is very tedious and error-prone. In the past, some students have also tried to use Terraform to improve the automation for deploying the application on cloud. However, they use a mixed approach by using both Terraform and YAML files. And as you can see, there's only limited usage of Terraform, which is hard for us to achieve a full automation. Also, to better manage the software development lifecycle, we need to create multiple environments that could allow us to thoroughly test the application at different stages of software development and ensure smooth software deployment. So, we propose a solution that involves managing everything, including the infrastructure, Kubernetes resources, and application resources using Terraform and Terragrant. This allows for a standardized and version-controlled approach to managing the infrastructure, making it more consistent, modular, and reusable. It also makes it easy to create and manage multiple environments and enables team collaboration. This figure gives you a high-level idea of creating infrastructure using Terraform and Terragrant. The developers will first need to create configuration files using Terraform, and we recommend them using Terraform modules to make everything modularized and reusable. The Terraform configuration files will be pushed to a standalone Terraform repository. Moving on, we'll be creating the Terragrant repository based on the Terraform code, which is also version controlled. With this solution, we'll be able to create a streamlined workflow for deploying the ASR application on the cloud platform that we use, AWS in this case. There are 3 steps in total to provision the resources that we need. In the first step, we need to provision the infrastructure-specific resources on the cloud platform. For example, the AWS EKS can help us create a managed Kubernetes cluster that we can deploy our application into. In the second step, we need to provision the cluster-specific resources required for the application deployment. For example, persistent volume, which is used to access the storage components that we provision in AWS to access our language models. And in step 3, with infrastructure and cluster ready, we're able to deploy the actual application and install some other required tools using Helm chart. It is very easy to create, easy to destroy, as everything is fully automated. Moving on, we want to talk about the implementation of our solution. There are 2 stages in this implementation. Firstly, we want to deploy the application purely with Terraform code. Secondly, we'll be integrating Terragrant and create multiple environments. In the first stage, we create resources using Terraform code. We will be creating configuration files with the .tf extension, and we will create one file for a group of resources. For example, we'll create a file called ekscluster.tf. And in these configuration files, we define the EKS cluster resource that we want to provision on AWS by using the Terraform module called EKS. However, as you can see that we put every file, everything, in one location. This might be okay for small projects or at the early stage of our project. However, this can be very hard to scale for complex projects. Imagine we have hundreds of resources to provision. We cannot create 100 files and put them in one location. This is creating barriers for developers to maintain as well. Also, this method can be very hard to read, as we cannot tell the resource structures from the file locations. And luckily, we have a solution, is to modularize related resources into logical units by leveraging the Terraform modules. As you can see, we grouped related resources that we want to provision into a standalone Terraform module. And immediately, you can tell what resources that we will be creating from the front structure. For example, we have AWS for the AWS resources for our cloud infrastructure, and we also have Kubernetes, which contains configurations for the cluster resources. This method is way better to manage. With the modules ready, our next step is to apply those changes by running Terraform command. There are 3 commands available for us. Terraform init, which is used to download dependencies that is required by Terraform. And Terraform apply is used to plan the resources that we need to provision according to the desired state that we defined in our configuration files. After our confirmation by typing yes, Terraform will be provisioning resources according to the configuration files. If the project is no longer in use and we want to remove those resources for our infrastructure, we can use the Terraform destroy command to clean up everything. In our implementation, we also make use of Terraform Cloud. With Terraform Cloud, we're able to upload our state files to remote locations, which can be shared for team collaboration. Now we're happy with the Terraform deployment. We want to move on and create multiple environments. And this is exactly where Terragrant comes into play. To use Terragrant, we'll be creating a separate code repository to store only Terraform code. In this repository, we'll be creating one directory for each environment. For example, the production environment, the development environment, and a stage environment. Some common values and configurations can be shared across multiple environments. The usage of Terragrant is pretty straightforward and simple as well. We'll be creating configurations that are specific to our environment. For example, we'll create environment-specific configurations, such as the environment variable here. And in the main entry files, there are only 4 major components that we need to care about. Locals defines the local variables that we need to use in Terragrant files. The Terraform block defines the source of our Terraform code that Terragrant is based on. In the inputs block, we'll provide the variables that are needed by our environment. And Terragrant also allows us to generate codes automatically to avoid manual repetition. For example, we can generate the package configuration to connect to our Terraform Cloud workspace. The Terragrant commands are similar to those of Terraform. Terragrant init for initializing the working directory and download dependencies. Apply is used to apply and provision the resources. And destroy is for cleanup. However, although Terraform and Terragrant can help us cover about 99% of the work for provisioning the infrastructure, there are still some resources and operations that are not covered by them. For example, we need to mount the EFS file system using an EC2 instance so that we'll be able to upload our language models to the file system that our worker nodes will be able to access. And the solution is also simple as well. We'll be able to automate the process by using a shell script to run the commands on our behalf. Next, we'll demonstrate the application that we deployed using this workflow in the proposed solution. In our terminal, we can try to access the service using the HTTPS protocol. As you can see, the protocol returns the hello message, which is defined by the application. And then we want to try the transcription service. And this is done by running the Python program of the ASR application. Let's try it. As you can see, we can access the transcription service by using the WebSocket Secure protocol, and it is generating text based on the audio file that we upload. Next, we want to take a look at the Kubernetes dashboard deployed for our cluster. And Kubernetes dashboard provides us with this web UI to navigate resources that we want to view. For example, if we click on cluster, we'll be able to get cluster resources in the web UI. As you can see, we have multiple namespaces, and we have one node that is running. Let's check out a node. This node is provisioned on AWS, as you can see from the name of this node. In the Kubernetes dashboard, we'll be able to see the allocation of resources such as CPU and memory. We also have Grafana, which provides dashboards for us to view the running status and monitoring the performance of our Kubernetes cluster. For example, if we choose dashboards, and we can select some dashboard, let's choose the cluster. As you can see, it's showing the performance of our Kubernetes cluster. We will be able to see the CPU usage, the CPU quota, the memory usage, and more. Now, let's conclude this project. The proposed solution improved the deployment process of the ASR application by using a workflow that automates the infrastructure resource provisioning using Terraform. The solution also made it easy for developers to deploy the ASR application on cloud for multiple environments that can help with the development and release lifecycle by using Terragrant. For future improvements, we can try to leverage the before, after, and error hooks offered by Terragrant, which provides us abilities to run some extra scripts before and after running Terragrant apply. We can also try to implement an auto-retry for running Terraform or Terragrant commands, as Terraform commands can fail from time to time due to the limitation of checking the dependencies across different cloud resources. Also, although the solution should be universal for all cloud platforms, we only tried AWS due to time limit. In the future, we recommend exploring the solution with other cloud platforms such as Microsoft Azure and Google Cloud Platform. Thank you and have a nice day.